All right, we are going to continue on with our discussion of metabolism, moving into respiration and fermentation in Chapter 9. We'll start here with Concept 9.1. Catabolic pathways yield energy by oxidizing organic fuels. This is going to take a second to stop and digest exactly what we mean by oxidation. So, catabolic pathways release stored energy by breaking down large complex molecules. A big part of this is the transfer of electrons from one molecule to another. This process is what we refer to as, this electron transfer is central to cellular respiration. Now, we already know that the breakdown of organic molecules is exergonic, and there are a couple different ways that we can get from this exergonic reaction to ATP. One is through this process called fermentation. This is a partial breakdown of sugars that occurs without the use of oxygen. There's a secondary process called aerobic respiration, which finishes breaking down these compounds and strips even more electrons off of it, and ultimately transfers those electrons onto oxygen. This process is what generates the vast majority of our ATP. There are anaerobic or respiration processes that don't use oxygen. So aerobic means uses oxygen, anaerobic means does not use oxygen. In these systems, they essentially work the exact same way as aerobic respiration. It's just instead of dumping the electrons off onto oxygen at the end, we dump them onto something else. Now, cellular respiration includes both aerobic and anaerobic respiration, but oftentimes we kind of limit our discussion to aerobic respiration. Why? Because it's pretty much only prokaryotic organisms that carry out anaerobic respiration. Anything eukaryotic is pretty much restricted to aerobic respiration. And although all carbohydrates and fats and proteins can be consumed as fuel, we are going to essentially only trace the simple sugar glucose through this pathway. And this is useful because most of the other things enter into this pathway that we're going to be viewing. So somewhere along the lines, fats will come in. Another place, amino acids might come in. Another place, other carbohydrates come in. So understanding this uh, usage of glucose is a good overall central pathway. So here we have glucose, which has 6 carbons, and we are going to utilize 6 oxygens in this process, and we are going to end up with 6 carbon dioxides because we had 6 carbons to begin with. We are also going to generate 6 water molecules, and in the process we will generate energy both in the form of chemical potential energy in the form of ATP, but we'll also produce heat along the way. So the key part of these reactions is understanding these processes of oxidation and reduction. So this is all based on the idea that we are going to be transferring electrons from one molecule to another molecule. And this transfer of electrons is essentially going to also transfer and release energy as well. This released energy is ultimately used to make ATP. Now, to start off with, let's kind of define what we mean by this. So when we have an oxidation-reduction reaction, both oxidation and reduction occur, and we oftentimes refer to these set of reactions as redox reactions. So what is oxidation and reduction? Well, oxidation is when a substance loses electrons. So when something loses electrons, it has undergone the process of oxidation, or you can say that it has become oxidized. In reduction, this is referring to the substance that gains those electrons that were lost over here. So reduction is the process of gaining electrons, and we can say that this molecule has become reduced. I realize that this is a confusion point because reduction seems to imply less, but we are actually gaining electrons. So try not to get hung up on that. Now, this idea of redox reactions we've already encountered, we just didn't call it that. So here we have sodium, here we have chloride. We know sodium has one more electron than it needs. If it loses one electron, then it can have a full outer shell that is the next level down. Chloride has 8 valence electrons and it just needs to gain one. So in this process of forming an ionic bond, you transfer that electron to the chloride. This results in a sodium cation and a chloride anion. So when we put it in terms of oxidation reduction, the sodium has become oxidized, it has lost an electron, and chloride has become reduced or gained that electron. So to put this in a more formulaic representation, we can have any molecule that has this electron, and we can have another molecule. When we move that electron from one molecule to another, here X becomes oxidized and it has lost that electron. Y has become reduced, gaining that electron. Now, another thing that that you might come across, and in chemistry we'll go into much more detail about this, is this idea that there are reducing and oxidizing agents. This is just simply a different usage of the words or kind of a play on it. So we know that X is going to become oxidized, and it is becoming oxidized because it is in the presence of Y, which is an oxidizing agent. Conversely, Y we know is going to become reduced, gaining an electron. It's only doing this because it is in the presence of a reducing agent. So we aren't going to get too hung up on the idea of reducing agent and oxidizing agent. We'll mostly be interested in the idea of oxidation and reduction. And I'm going to try and focus in on the molecules that are becoming reduced. So what is gaining the electrons in the reaction? So here, if we start looking at glucose, it is becoming oxidized, so it is losing lots of electrons, and all of those electrons are being dumped onto oxygen. Oxygen is becoming reduced to water. Okay, so if you start adding electrons onto oxygen, you turn it into water. Now you'll notice that in this process, that water has gained some hydrogen um, atoms too. This is because the protons that are ultimately associated with the electrons that are being moved tends to follow. Okay. You'll also notice here that the carbon is going to be now bound to oxygen. This is kind of where the term oxidized actually comes from. The fact that the compound is now in some type of combination with oxygen atoms. All right. Now, when we transfer electrons, we just can't let electrons float around in space. That works great for protons or hydrogen cations, but that doesn't work for electrons. Electrons have to be associated with something. So we have this compound called NAD+. And this NAD+ is going to act as an intermediate carrying electrons from one place to another. So here in cellular respiration, glucose is broken down. We strip those electrons off. Those electrons get put onto NAD, and in this chemical reaction, NAD is operating as the oxidizing agent for glucose. And each NAD molecule that becomes, or NAD plus molecule that becomes reduced, becomes NADH. Okay, so the NADH represents the reduced form, so with electrons, without electrons. And this is something that we can then utilize later on to help generate ATP. What does this look like? Well, this is NAD+. You might recognize part of this. This right here is ADP. So ribose, adenine, and 2 phosphates. Here, this part of the molecule is simply acting as a handle so that various proteins can hold on to something. The same thing is true of ATP. The phosphates are where the energy is stored. The rest of the molecule is just acting as a handle. So here, this nicotinamide structure is what's actually going to hold the electrons. And don't get hung up on knowing this or remembering this, but just so you've seen it, this is what it looks like without those electrons. When you move 2 electrons onto it, it'll go into this ring-shaped structure and associated with this nitrogen. And you'll also notice that protons come along with this. One of the protons is actually linked onto the ring. And the other proton is just kind of following it, or just existing in space around it. Now, NAD is a useful molecule. It can also be used to change other molecules. So here we have a carbon with a hydroxyl functional group. If you put that in the presence of NAD with the right enzyme, you can essentially oxidize this hydroxyl and it will become a carbonyl. Okay? And now we have a reduced form of NADH. This could also work in reverse in that you can have NADH dump electrons onto a carbonyl and turn it into a hydroxyl. Again, not something you need to know, but later this will come in, or in much later courses, this will come in handy. Now, when we are breaking down molecules and utilizing the energy, we can kind of think of it of how it looks in space, right? So here, what we have is hydrogen and oxygen. And this is the components of a fuel cell. So if you take hydrogen and catch it on fire, it will start carrying out a redox reaction, resulting in the formation of water. This is a very explosive reaction that releases a lot of energy all at once. What we do is, instead of going directly from here to here, what we do is we take the electrons off of the hydrogen. We can then dump those electrons into something called an electron transport chain, which is essentially transferring electrons from one thing to another, to another, to another, to another. We can utilize this transfer to do work. Then ultimately those electrons are dumped onto oxygen, producing water. So here we're harvesting that energy